Welcome back, everyone. This is the second segment of section 5.5. As you recall, we had derived all of the double angle formulas for sine, cosine, and tangent, and showed a real simple application before we basically ran out of time. So what I'm going to do now is I'm going to work through a couple of sort of standard problems from this section. That are what I would consider to be applications. You know, there's some statements about a situational setup, and then we proceed to the solution. So with no further ado, I'm going to kick us over here to work on the document camera. Try to get my modernized Pink Floyd background off here. Okay, so I believe we are now on page 3. And here's kind of how we're going to set this up. So as you know, we've done a number of problems where we know something about a function of an angle. We know something about the quadrant that angle might be in, and then we try to find some other values. We're gonna do this in a direct application of the double angle formulas. So let's write this problem this way. So given sine of theta equal to 8/17 and cosine of theta less than 0. Find a couple of things. Let's find first what the sine of 2 theta is, then cosine of 2 theta, tangent of 2 theta, and lastly, sorry, this is C, lastly, quadrant of 2 theta. Okay, so let's just pause a minute and think about how we're going to approach this. Notice that the only formulation we have for sine of 2 theta involves sine of theta, which we do have, and cosine of theta, which we do not. The only formula we have for tangent of 2 theta involves tangent of theta, which we also do not have. So as some preliminary work, it would make sense for us to find, using this problem, right, the statement of this problem here, like we've done in chapter 1, let's find cosine of theta and also tangent of theta. So to help us out with that, note that we have this statement about cosine of theta is negative. So we need to figure out what the quadrant of theta is first, and then establish the other two trig values. So let's do that. First, find quad of theta. Now we've done this enough that I don't really need to get real crazy with this, but sine is positive in quadrant 1 and 2, and cosine is negative in quadrant 2 and 3. So where those overlap is actually is quadrant 2. So this tells us theta, that's just sort of a statement, theta is in Q2, which the only reason we really did this is to find the SIGN of tangent, which we probably could have surmised from just the value of the cosine, but this is not something that, I mean, this is pretty standard how we've done it before. So with this information, the value of sine and the quadrant of theta, sine of theta and quadrant of theta, we can find all the trig values, but we only want cosine and tangent because that's all we're going to end up using in this solution. So recall, and since we're trying to use these sort of better techniques, but what I've said is, if you have a statement of a problem like that, it really makes sense just to draw the angle in the appropriate quadrant and just start attaching coordinates to a point on the ray. So let's do that. I mean, let's do things the easy way. So here's our coordinate axes. Here's our angle in quadrant 2. And we know that there's a point out here, P, where based on the value of sine, y will be equal to 8, and the distance will, or r will be equal to 17. So I've got 8. I don't know what x is yet, but r is equal to 17. So y, kind of do a little scratch work here, y is going to be equal to the square root of r squared, sorry, not y, we're looking for x, plus or minus the square root of r squared minus y squared. And note, we already know from which quadrant this in that it's definitely going to be negative. So this is going to be negative square root of, what's 17 squared? Is that 349? Gosh. 17, 4, 19, 289. Okay, so 289 minus 64 will be equal to the negative square root of 225. Now, it just so happens that I recognize that as a perfect square. This will be equal to negative square root of 15, or sorry, negative 15. So that tells us that and I've got these backwards up here. So just to summarize, we have x equal negative 15, y equal 8, and r equal to 17. So we can now compute, we had sine, let's find cosine and then find tangent. So sine of theta is already given as 8 over 17. Cosine of theta, well, that's just going to be x over r, so that's equal to negative 15 over 17. And then finally, tangent of theta, I'll put it right here so we can kind of box them all, is going to be equal to y over x, or negative 8 over 15. So this is sort of the preliminary work that we needed to do in order to be able to answer these first 3 parts. Okay, and I'll refer back to them as necessary. But I think we can do part A relatively quickly because sine of 2 theta, recall, has a formula that is just 2 times the sine of theta times the cosine of theta. And simple substitution will get us 2 times, well, sine of theta is 8 over 17. And cosine of theta is negative 15 over 17, which happens to equal, well, let's see, 8 times negative 15 is going to be a negative 120. So double that. What's that going to be? Double that's going to be negative 240. Sorry. Ooh, sorry. Over 289, which we found is the square of 117. So there's our first bit, and I'm pretty sure that can't reduce because the only factors in 289 are actually 17. So unless this was divisible by 17, this is a fraction in least terms. Okay, so let's move to the rest of those problems. I'll refer back to that in just a second. So part B, we wanted to find cosine of 2 theta. Now, we could use any one of the 3 formulations for cosine of 2 theta, but since we were given sine of theta in the problem, I think maybe it makes sense to use the so-called second version, which is 1 minus 2 times sine squared of theta. I mean, we could use any one of them because we have all the appropriate functions now, but this one seems to work as good as any. So referring back, it was 1 minus 2 times 8 over 17 squared. Remember, sine of theta was 8 over 17 originally given in the problem. So this becomes, since I'm going to have 289ths, I'll have 289 over 289. This is going to be 64 times 2 will be negative 128 over 289, which results in 161 over 289. So there's your cosine of 2 theta. At this point, we could use just the fact that we know sine of 2 theta and cosine of 2 theta to complete this problem. It's up to you how you want to do it. I think that maybe there's a slight advantage to using that formulation, but just to familiarize ourselves with with these new equations that we've come up with, I'll go ahead and use the formulation for tangent of 2 theta. So recall we're going to want to find tangent of 2 theta. And that's going to be 2 times the tangent of theta over 1 minus tangent of theta squared, tangent squared of theta. So recall, let's pull this right back up again. Remember that the value of tangent of theta is negative 8 over 15. So we have in the numerator 2 times negative 8 over 15 all over 1 minus negative 8 over 15 quantity squared, which is going to be equal to negative 16 over 15 over 1 minus 64 over 225. Now this is at this point, this is a complex fraction, and recall that the best way to sort of kill off these complex fractions is to multiply top and bottom, multiply all terms by the least common denominator of all interior fractions, which happens to, this is 15, it's one of our denominators, and this is just 15 times 15. So the least common denominator here, let's maybe put this over here, is 225. So I'm just going to end up multiplying top and bottom by 225. So the top, this is going to get a little ugly. It's going to be, well, this is going to reduce that by 15. So it's going to be negative 16 times 15, which I'm not quite sure what that is right offhand here. Negative 16 times 15, 0, 3, 8, 1, 6, negative, so 2. I believe we've got 240 negative. So this will be negative 240 divided by 225 minus 64. Okay. Now you've seen this already. Well, maybe not. 225 minus 64. I think this is going to get us back to that 161 again, which we've already seen. So we end up with minus 240 divided by 161. Now, like I said, we could have gotten that from just the cosine of 2 theta and sine of 2 theta directly, and we could check it just to make sure we did the work right. But like I said, I wanted to play around with this tangent of 2 theta equation, just to make sure that everybody's real familiar with it. Now, from this, from all that information, we can pretty quickly figure out the quadrant of 2 theta, because note that looking back at the SIG ends, so for one thing, tangent, you could use any combination of these, but notice that tangent is negative, so it's either going to be quadrant 2 or 4. And cosine is positive, which says it's either going to be quadrant 1 or 4. The only real overlap there is quadrant 4. So 2 theta happens to be in quadrant. Okay, so that finishes out that problem. I've got another problem that I want to do that is kind of similar and does things in a different way, but I'll go ahead and since this isn't super long, you know what? I'll just go ahead and do this one as well, maybe with a little less commentary. But it's going to be similar in the sense that, you know, another way that we might think about doing this is if I know something about 2 theta, and then try to figure out things about the trig functions of, find the trig functions of theta. So let's just start by stating this problem here. So 5.5, this is kind of setting us up for section 5.6. So let's state it this way. Suppose that cosine of 2 theta is equal to negative 12 over 13. And theta in quadrant 3. Now, we could also have things where we talk about, you know, 2 theta in quadrant whatever. I mean, there's all kinds of different versions of this, but I think this kind of gets to the heart of it. So we want to find as many, I think we can do this fairly quickly. So find all 6 trig functions as a function of theta. So for example, we want to find sine of theta, not necessarily sine, and not sine of 2 theta. That's basically what this is saying. So let's start. I mean, there's many ways to do this because we have all of these interrelationships. But remember, we need, in order to solve this problem, all we minimally need is we need the value of any one trig function and the quadrant, right? So if we find, for example, sine of theta, and we know this about the quadrant, we can write the rest of them just by, you know, creating a diagram and putting a point out there on a terminal ray and solving it that way. But let's try to do it in a way that that uses some of these new identities, okay? Because I'm sure you know how to do it that way, and if you were pressed for time, that might be the most natural. But let's start by trying to find sine of theta. Now we have to use something that relates cosine of 2 theta to sine of theta. Unfortunately, there is an equation for that does that. We have cosine of 2 theta equal to 1 minus 2 sine squared of theta. And here we have an equation between these two functions. We know normally we know this we know the sine, and we're trying to find the cosine of 2 theta. But let's just rearrange this equation so that we're solving for sine. So first off, we're going to get 2 sine squared of theta equal to 1 minus cosine of 2 theta. Divide both sides by 2 and take the square root. So we end up kind of combining a couple steps there. So sine squared of theta is equal to 1 minus cosine of 2 theta over 2. So sine of theta is equal to plus or minus the square root of 1 minus cosine of 2 theta over 2. We're going to see that equation again in 5.6 because this is kind of how we go from something that has, we know a trig function of a certain angle, and then we break it down to half that angle. This actually is the half angle formula, just kind of in disguise there. Okay, so let's first recognize that since theta is in quadrant 3, we know that this has to be the negative branch, and then we just need to substitute the values of cosine of 2 theta. So sine of theta is going to be equal to the negative square root of 1 minus, and recall this was a negative sign, so be real careful with those negative signs. It's minus a negative 12 over 13 all over 2. So simplifying simplifying this complex fraction, I'm just going to multiply everything by 13. And what I end up with here is that it's minus square root of 13 plus 12 all over 26, which is going to be equal to negative 5 over square root of 26. There's a little bit of simplification. Now, we got to rationalize this denominator, so we're going to multiply by 26 over 20, square root of 26 over square root of 26, which just happens to equal negative 5 square root of 26 over 26, right? So there's our sine of theta. Now, like I said, we could use either one of these formulations, and because this is, we know that this is an angle in quadrant 3, and there's a point on that terminal ray that happens to have an R value of square root of 26 and a Y value of negative 5. But like I said, let's work with the formulas a little bit more just to see how that works. Okay, so I think we're on page 6 now. So the next step then is to find cosine. So recall, it's sort of a real similar thing to what we just had. We could go through that same formulation, but let me try using a different one. So cosine of 2 theta equal to cosine squared theta minus sine squared theta. And since I just found sine squared of theta, I'm going to just, you're going to see how this gets a little bit cleaner. So cosine squared of theta is equal to cosine of 2 theta plus sine squared of theta. And so cosine of theta equal to plus or minus the square root of cosine 2 theta plus sine squared of theta. Okay, so recall this is an angle in quadrant 3, so this is actually going to be the negative, and we know the values of these two things. So this is going to be what, negative square root of, well, cosine of 2 theta, recall, was negative 12 over 13. And the sine of theta was negative 5 over square root of 26 before we rationalized the denominator. So that actually makes this 25 over 26. Okay? And so simplifying this, we end up, we got to find a common denominator here. And the square root of negative 24 over 26 plus 25 over 26. That's pretty easy to do now because it's 1 over 26. We're left with negative 1 over square root of 26, a couple steps in there, which in order to rationalize that is the negative square root of 26 over 26. Okay. Now, at some point, we may want to start relying on other fundamental identities rather than going back to 2 theta every time, because now we had sine of theta on the previous page, and now we have cosine of theta. Why don't we just polish these off as quick as possible? So tangent of theta is sine of theta over cosine of theta, which is just, and I'm going to use them in their unrationalized form. So minus 5 over square root of 26, just because it's simpler, over negative 1 over square root of 26. So this is one of the ways we saw sine, and this is cosine of theta here, which happens to just be equal to positive 5. Pretty simple. Now, from here, we should be able to use reciprocal identities to do the rest of them. So let's go with cotangent. Well, cotangent of theta is just 1 over tangent. That's probably the easiest one to work with, which is just 1 over 5, right? And then we'll move on to secant. Well, secant of theta is just 1 over cosine of theta. And note, again, maybe it's a little more convenient to use this version because we can just reciprocate this with ease, whereas this one kind of adds some extra stuff we don't need. So this becomes negative square root of 26, right? And then finally, cosecant of theta is equal to 1 over sine of theta. And if you've forgotten what sine of theta looked like, I'll bring that back here a second. Notice we had, this is the fully rationalized version, but this is the one that's actually easier to work with. So I'm just going to reciprocate this term and it'll be all done. So this just flip everything upside down. We end up square root of 26 over 5. So this completes the problem. We now have given some information about one trig function of the double angle and the quadrant of the angle. We developed all 6 trig functions of the angle. All right, this is probably pretty long, so I'm going to get out of here. We'll be back with more problems.